again. But yeah, Alice, what'd you do? Since you said it was exciting. You went to the Met? Um, that's cool. How was it? Yeah, I can imagine. Yeah, so it has come to my attention that we don't have class on Thursday. So yeah, we're not meeting on Thursday. I think it's how it goes is tomorrow's a Friday schedule. I think that's what someone told me, and um, we're off Thursday and Friday. So yeah, next time we meet is next Tuesday. All right. So let's begin. Okay, this is the last time I'm doing this. So does anyone have questions regarding the homework? And as you know, last time I said that I'm gonna just drop all the homework from now on. So this is the last time we're gonna go over a homework section. So last chance. And then what was last section? 8.4, I think. Yeah. So anything regarding 8.4 that you guys want to ask? Are you still having office hours after the last class? Office hours. Oh, you mean like the that gap between like between the last class and the final, right? That 1 week period. um, yeah, sure. I'll have office hours. Just make sure you email me though, just because like I might forget. So yeah, but yeah, I'll have office hours. Can we do question 6? Okay, let me pull up the homework. When would office hours be? Well, the official hours were, I think, Tuesday before class, so Tuesday 4:10 to 5 something. But I mean, I'm flexible with it. So if you need like another hour, that's not that one, just email me and then I'll let you know if I'm available at that time. So yeah. Okay, let me see what question 6 is. All right, so here's question 6. All right, so um, this is an alternating series, right? So because it's an alternating series, my first instinct will probably be to try the alternating series test. Is that what you tried? Yeah, and did it work? Okay, that's fine. Let me just pull up the alternating series test formula or the information about it just so we can have it for reference. So give me 1 second. Screen. Okay, so here's the alternating series test. All right, so let's try it. We need to identify what's B of n here. So let's see. Let's use blue. So in this question, B of n is this particular part of the series, right? Okay, so we need to check two conditions. So number one, does the limit of B of n go to 0? I think it already failed. So I think the limit here goes to 2 or 5, right? And approaches infinity of B of n. Limit and approaches infinity. So this is 2 over 5. So the alternating series test already failed. So now we need to do another test. What do you think? Do you have any suggestions? This failed. You want to try the, what's the other one? The divergence test? Because I know that one's easy. Yeah, let's try the divergence test. So let me pull up the information for divergence test. Okay, so here's the divergence test. Let's try that one. So in this case, we need to find the limit of basically A of n. A of n is the whole thing, including the alternating series sign. So we want to see what happens when we take the limit as n approaches infinity of A of n. A of n is actually the whole thing. So this is A of n here. So what would the limit here be? Now, the way we analyze this is that we sort of just analyze it in parts. So analyze this part first and then analyze this part. So we already did the right part. We know that the limit of this part goes to 2 over 3, right? I mean 2 over 5. And then we want to think about what this negative 1 to the n does. So the negative 1 to the n just makes the terms in the series alternate signs. So what this is saying is that as you go further and further in, your terms get slowly closer and closer to negative 2 over 5, positive 2 over 5, negative 2 over 5, and positive 2 over 5. So this is the pattern of A of n, right? This is, there's a lot of terms in the beginning, but as you go further and further in, this is what your terms are approaching, right? As n goes infinity. And then you can sort of see that as you go towards the end, you don't actually reach a particular limit, because you know how like for sine and cosine, you don't have a limit because it's like alternating between negative 1 and 1. So this is the same idea here. So based on this analysis, we can say that the limit does not exist. Okay, so that would be your answer for this part, DNE. And then since the limit does not exist, yeah, so does not exist means that the limit was not 0, so therefore it diverges by the divergence test. Okay. So this diverges. Okay. Yeah, no problem. All right. Anything else? If not, then I'll start today's lesson. Can we do 8? Let me see. So I did withdraw question number 8 because there is a part of question number 8 that is asking you about something that we didn't learn. So I would prefer not to do number 8, but if you, we can go over the first part if you like. Is that something you want to see? Okay. Because the first part is something that you can do, but not the second part. So this is question number 8. Crop this. So yeah, this is the part that led me to withdraw this question. So we will do just this. Actually, wait, no. You can do up to here, actually. Yeah. All right, let's take a look. So again, you see that's an alternating series, right? This is 8.4. Were you referring to number 8 in like a different section? 8.5. Yeah, so okay, that's okay. Yeah, so 8.5 is optional. Any homework that's 8.5 or later is do it anyways. Are you sure? Okay, so this is an alternating series, which means the first thing you should try is the alternating series test. So alternating series tests say identify B of n. In this case, B of n is 1 over 2n and factorial. First thing you want to see is whether or not the limit of B of n as n approaches infinity goes to 0. So as you plug in a really high number for n, does this go to 0? I think it's obvious that this one does because it's just the 1 in the numerator. So limit as n approaches infinity of B of n is equal to 0. And then is B of n decreasing? So let's see, 1 over 2 to the 0, 0 factorial, 1 over 2 to the 1, 1 factorial, comma, 1 over 2 squared, 2 factorial, so on. Yeah, I think I'm convinced this is decreasing. But yeah, let's see what the question wanted. Yeah, they just say identify B of n, which we did. And then the limit of B of n was 0. And then since the limit of B of n is equal to 0 and the next term is less than the previous term, that means it's decreasing. Then the series is convergent. Yeah, so this is convergent. Okay. Because I didn't officially assign 8.5, we're not going to go through that. If you really want to see something from 8.5, you can just email me after class and I'll answer it for you, okay? All right, let's start today's lesson. So we did power series last time, right? Okay, can I get a confirmation on that? We did power series last time. maybe. Okay, so yeah, power series was the series where like um, it has x's in it instead of just numbers. So we're going to continue on that. Today's lesson is representing functions as power series. So what do I mean by that? So there are some functions that we know where it can actually be rewritten as a power series. So the question is, well, why would we even want to do that? So the answer is actually because the way power series are, how they're like is they're most of the time power series are like a polynomial, right? Because it has terms with x's of power. And polynomials have some really good properties. So they can like, they're easy to take derivatives of and they're easy to integrate and all that stuff. But at the same time, like it's a series. So you can apply your knowledge of series to do stuff with functions. So that's really the main reason. Okay, so let's look at a future of previous topic that we learned, which was geometric series. And do you guys remember this formula over here? This series a times r to the n equals a over 1 minus r. So this was the formula we learned for the sum of an infinite geometric series, right? Which says that if you have an infinite geometric series, which is the left-hand side of the equal sign, then in order to find the sum of that series, it happens to be the first term divided by 1 minus the common ratio, right? And this formula only holds as long as your common ratio is less than 1. So hopefully you guys remember that. So next thing we're going to do is we're actually going to make some substitutions in this formula. So if we let a equals 1, so in other words, if you let your first term in your series equal to 1, and you use the letter x in place of the common ratio, then your formula looks like this, right? You get series x to the n is equal to 1 over 1 minus x, provided that x is less than 1. So the reason why we did this substitution is because now the left side of the equation, the series part, that is actually a power series now. Do you guys see that? X to the n, that's a power series. So what did we just establish? Well, the left side is a power series, but the right side is 1 over 1 minus x. You can sort of look at the right side as like the function 1 over 1 minus x. So the conclusion is that if you have a function in the form 1 over 1 minus x, you can rewrite that function as a power series. So you can rewrite it as summation of x to the n. So let me explicitly write out the terms just so we know what this all means. So we have just concluded that 1 over 1 minus x is equal to this power series, which is 1 plus x to the first power plus x squared plus x to the third plus x to the fourth, and so on. So that's what we just figured out. So what do you guys think about that conclusion? Do you guys find that result surprising? Kind of. What do you find surprising about it? I think it's kind of surprising because we're basically saying a rational function is actually the same as some weird polynomial. So recall that this or this equality, this equal sign, only holds for x values that are less than 1, right? So this equation doesn't hold for every value of x. This equation only holds for certain values of x. So if I let x equals like 0.5, this equation will hold, right? These two sides will be equal. But if I let x equals like 1.5, then this is not going to be equal anymore, okay? How do you get every power of x? That's just the power series. So this power series here, I just wrote out all the terms for this power series. So instead of writing it like in a summation, I just wrote out each term. That's crazy. How is that crazy? All right, so let me switch back to the PowerPoint. Okay, so next thing we're gonna look at is some graphs. So we just established that 1 over 1 minus x is equal to 1 plus x squared plus so on and so on and so on, right? So let's go to a graphing tool and let's see what that looks like. So first I'm gonna graph 1 over 1 minus x. There it is. So that's a graph of 1 over 1 minus x. And then now let's graph the power series to make sure that it's the same graph. But I'm not going to put the whole power series because that's just impossible. There's like an infinite amount of terms. So let me just go one term at a time. So the first term was 1. Okay, that didn't do anything. Let me put another one, x. Okay, so what do we notice here? So the blue graph is the power series, and then the red graph is the 1 over 1 minus x. So if I just put two terms of the power series in, they're obviously not the same, right? You guys can see that one is a line, the other one's clearly not a line, so this is not the same. But let me put more terms in. So plus, what's the next term? X squared. Okay, so what do you guys notice just happened here? Closer to the red line, it's fitting better. Yeah, so we made it a parabola, which sort of made the curve adhere a little better to the red graph. Let's put in more terms. So the next term was x to the third. Okay, what happened now? So I add another one. Did it make it even better? Let me see. This was x squared plus x to the third. You can type in sum, by the way. I did not know that, but we don't want to type in all the terms, actually. We just want to see what happens as you add one at a time. Let me go x to the fourth. Yeah, so I think you guys get the point. As you put in more and more terms for the power series, it more closely matches the original function, okay? All right, so notice how right now it closely matches up to a particular x value, right? So right now it sort of matches up to like x equals like 0.5-ish, and then it starts to like not match anymore. So let me ask you guys this. As we add more terms, it'll closely match it'll match more closely, right? But do you guys think it will, I can put it enough terms to say like, make it match past x equals like -1? So let me add in more terms. Plus x to the fifth. So now it's like a little bit past 0.5. Let me add plus x to the sixth. So now it's a little bit better, but it's still not a -1. Do you guys think I will be able to reach -1 if I keep adding more and more? Okay, it's a little better. That's where it fails. Why would it fail? What's wrong with -1? Crap, I did not mean to do that. Plus x to the eighth. Yeah, very good. So recall that the relationship we established is that the two sides of the inequality, or two sides of the equality, only hold when x is less than one, right? So it's actually never going to be the same function past -1 or +1. So yeah, you can only get it to match the red graph from uh, from here to here. Well, one kind of makes sense because there's an asymptote there. Yeah. Okay. So that's the graphical representation. You're basically trying to approximate another function with a power series. So yeah. Okay. So now we're going to do problems. You guys will see what problems in this section look like. Next one. So how this is going to work is we're going to want to write a function in the form 1/1 minus x. And then once we get it in that form, then we can use the power series formula. Okay. So let me show you how that looks like. Paste. This is the example. And then put the screen. Okay, so this is what we need for all these questions. Let me crop this. Okay. So we know that this is the formula we need for all these questions. This equation here, g of x equals 1/1 plus x to the third. So that's obviously not in the form 1/1 minus x, which means we can't really use this relationship here. But we can actually get it in that form. So observe what I will do right now. So instead of writing 1/1 plus x, I'm going to write 1/1 minus negative x to the third. Do you guys see what I just did there? Are you guys okay with that? Yeah? Yes? Okay, good. So now that I have rewritten it like that, do you guys see how it's in the form now? So it's in the form 1/1 minus something. So because it's in the form, I'm going to say this a lot, so I'll just call this the form, okay? So this is, we're going to call this the form. So right now it's in the form, right? So because it's in the form, we can apply the power series formula. So we can say that g of x is equal to this power series, n equals 0 to infinity. So in this particular question, x is basically, label it with a different color. X is basically this part here, right? So then it would also go here. So our power series will be negative x to the third to the nth power. provided negative x to the third power is less than 1. Is everyone okay with that? Okay, this is also an x. So I just replace x with whatever I have in the parentheses here. So in this case, the parentheses was negative x to the third. All right. So there you go. This is the power series representation for g of x. I hope that's fine. And then the question also wants us to determine its interval of convergence. So the way we do that is we just use basically this condition here. So this condition here. We will use that inequality to determine its interval of convergence. So let's solve this inequality. Dealing with the absolute value sign, you're going to get x to the third is less than 1. And then, so x is less than 1. Let's just take the cube root of both sides. Actually, did I do that right? No, I didn't do that right. Sorry. So it's actually the absolute value cubed is less than 1. So therefore, the absolute value of x is less than 1. Which means your interval of convergence is negative 1 to 1. Because this becomes x is less than 1 or x is greater than negative 1. So this is your interval. Okay, so this is your interval of convergence. Just call it I. All right, so just to recap, our function g of x is 1 over 1 plus x to the third. The power series representation for this function is summation of negative x to the third to the nth power, right? And this power series will only represent g of x if if we choose x values between negative 1 and 1. All right, so that's the summary. Any questions on that? Don't we have to test if it's bracket or parentheses? Oh, yes, good question. So we do not actually, because this this condition here is strictly a less than sign. So we do not have to test it. The reason why we had to test it before is because in the last section, we were using the ratio test conclusion. The ratio test says that if the limit was equal to 1, it's inconclusive, which is why before we had to test it. But now we're not using the ratio test anymore. We're just using like the rules for a geometric series. So we don't need to test it anymore because this is strictly just a less than sign. Okay, let's move on. All right, so here's another example. This one has the same directions and then it's a different function. Okay. So let's try this one. Yeah, so remember that when regarding functions in power series, you don't need to test the endpoints. All right. Here's question number 2. Let me just copy this. Okay, so all these questions are going to have a similar process. You want to get it in the form 1 over 1 minus x. So right now it's not in the form, right? So we have to get it in that form. Um, first thing I'm going to do is I'm going to rewrite it like so. H of x is equal to 2x squared times 1 over 1 plus x to the third. Is that okay, guys? Yes? Okay, great. So now that we have it in that form, uh, I'm going to focus strictly on the parentheses part. So h of x is equal to 2x squared, 1 over 1 minus negative x to the third. Actually, this is like the same thing we had last time, right? This parentheses part. So we want to find a power series for this. Now, we kind of already did that for the parentheses part, so let me just replace it. So h of x is equal to 2x squared times this power series, n equals 0 to infinity of negative 3, negative x to the third to the nth power, provided negative x to the third is less than 1. Is that okay? All right, so let's see. Well, we already solved this inequality, right? We know this inequality is going to become negative 1, comma 1. So that's our interval of convergence. The power series representation, you'll notice that right now there's a 2x squared in front of the series. So technically there's nothing wrong with that. However, when we talk about power series representations, the simplest form is usually in the form where there's only one x variable. So we sort of want to just write this in the simplest form. So let me try doing that. I'm going to bring the 2 back inside. So this is that. And then I have 2x squared negative x 3 to the nth power. Let me see what is in the second line. Is the q supposed to be on the inside or the outside of the parentheses? It is supposed to be I'm pretty sure it's on the inside. I think in this case it doesn't really matter, but I just chose to put it on the inside. I mean, you sort of want it on the inside because you want to clearly identify what this part of the formula is. Okay, well, yeah, I erased it, but I meant to put it on the inside. You want to put it on the inside here. Because that way we can clearly see that the x part of our formula is negative x to the third. Okay. All right, I'm going to continue simplifying this. So what do we have here? So it's n equals 0, infinity I'm gonna have 2x squared. I'm gonna break the negative out, so negative 1 to the n, and then x to the 3n. So now I'm gonna combine the all the x's together. So n equals 0, infinity. This is 2 times negative 1 to the n, and then x to the 3n plus 2. Okay. All right, so this is the, I guess, the most simplified form. Let's bring that down. So there you go. Our function is 2x squared over 1 plus x cubed. And then the power series representation for this function is the following. So it's 2 times negative 1 to the n times x to the 3n plus 2. Okay? And our interval of convergence is any x value between negative 1 and 1. Does this strat only give the interval? The interval of convergence? Well, what else would you want here? I mean, you mean like the radius of convergence? Negative 1 to the n. Yeah. Do you have a question or something about it? I did my algebra right? I hope this is fine. Okay. All right. Yeah, so most of these questions have the same process. We can do more tests after this. You mean like to see whether it converges or diverges? Well, remember, it's a power series. So power series will converge or diverge depending what values of x you use. So this interval of convergence tells you what x values will make it diverge. So if you plug in a number between negative 1 and 1, it will give you a convergent series, which you can verify using some divergence tests. But yeah. Okay, let's continue. So is the interval always negative 1 to 1? No, it's not always negative 1 to 1. In fact, I think this next example will give you a different interval. Yeah, so let's try it. Let's look at this one. All right, then let's copy and paste. We need to have this here. Okay, so first thing you notice is that this is not in the form that we want, which means we need to get it in the form that we want. So let's do that. We can factor out the x. So this is x over 1 over 5 minus x. So just focusing on the parentheses part, the 1 over 5 minus x, that's still not in the form that we want, right? We want to have a 1 instead of a 5. So what can we do? What we can do is we can actually factor out a 5 from the denominator. So if you do that, you will be left with 1 over 1 minus x over 5. Is everyone okay with the algebra there? Okay, so uh, now you'll notice that it's in the form that we want because this is 1 over 1 minus something. So what is that something? So it's basically this, right? That's your, I guess, your quote unquote x. So because this is a form, now we can write it as a power series. So this is equal to x over 5. That can just stay there. The power series from n equals 0 to infinity of x over 5 to the n, provided absolute value of x to the x over 5 is less than 1. Okay. Okay, so let's see. Yeah, this is fine. So this is the power series representation. And then let's find the interval of convergence first. So let's solve this inequality. We will have absolute value of x is, if I factor out the 1/5, absolute value of x is less than 1. And then I have absolute value of x is less than 5. So you guys can see that in this question, the interval of convergence changed, right? So here we're going to actually have -5 to 5. All right, so there's our interval of convergence for our power series. We're going to do a little more work on the power series, right? Because this is not in the most simplest form. So let's try to bring everything inside and let's combine all the x's together. So first I'll write it as with the x over 5 inside times, this is x to the n times 5 to the n, right? And then this is x to the n plus 1 over 5 to the n plus 1. Okay, so there you go. So here we have the power series representation for our function, and then this is the interval of convergence. So how do you guys feel about this so far? Not bad, good. Okay, yeah, I don't think this is too bad. Really, you just need to memorize this formula here. So 1 over 1 minus x is this power series. Okay, let's continue. Okay, so in the last 3 examples, the way we got our function to be in the form is we just used algebra. So apparently that's not the only way you can do things. There's actually more techniques than just, moving stuff around and factoring things out and rewriting it. There are questions that will require you to do derivatives and integration, unfortunately. So it's gonna be weird, but yeah. So let's just read the slide first. So far, we have used algebra to get a function in the form that we want. However, we can also use differentiation and integration. The interval of convergence stays the same when you integrate / differentiate a power series. Okay, that's good to know. Let's look at an example. So let's look at this function over here. Okay, so here is the example. We have g of x equals 1 over 1 minus x, the whole thing squared. So clearly it's not in the form that we want. But how can we get it in the form that we want? Any ideas here? Can you split it up into two fractions? Separate it into two fractions. You can, but there's an easier method. Think about the slide we just looked at. Yeah, I mean, you could do all those things, but there's actually a method that like is even easier than all of that. So here's a hint. How does 1 over 1 minus x squared, how does that relate to 1 over 1 minus x? What is the relationship between these two? Yeah, but there's actually another one. There's another connection besides that. Yes, besides that. All right, I hope you guys are a little more. So, what happens when you take the derivative of 1 over 1 minus x? So what happens when I do this? The derivative of 1 over 1 minus x. What is this equal to? The other value. Yeah, the other function, right? So let's just verify that. So in order to take the derivative here, we need the quotient rule. So that's the bottom times the derivative of the top minus the top times the derivative of the bottom, which is -1, all over the bottom squared. So this is -1 times -1, that's 1 over 1 minus x squared. Okay, so yeah, 1 over 1 minus x squared is basically the result of taking the derivative of 1 over 1 minus x. So what does this mean? It means that we can actually rewrite our function g of x. Instead of writing it like this, I can write it as the derivative of 1 over 1 minus x. Do you guys see that? I mean, you guys offer a lot of suggestions. All of them are correct, but as far as achieving what we want to do, which is to find a power series representation, this is actually the best suggestion. Okay. So, yeah, 1/1 minus x. Do you guys see that that's in the form now that we want, right? So we can use the formula for a power series. So g of x is equal to d dx of 1/1 minus x, which we can rewrite as summation n equals 0 of infinity of x to the n. Right? This is just the regular one. This is not like a different one. Provided absolute value of x is less than 1. Okay, all right, is everyone okay so far? I know it wasn't quite obvious that this is the derivative, but hopefully with this like work on the side, you guys are okay. All right, so let's just deal with the inequality to get our interval of convergence. So I is, in this case, it's -1 to 1. Yeah, all right, now let's simplify our power series. So let's think about what this means here. We are taking a derivative of a power series. Do you guys remember how to do that? How to take the derivative or the derivative of power series? Like how would you take the derivative of a series in general? You know, because a series is not just one function; it's like the sum of many functions. Well, it's actually not that complicated. All you have to do is just take the derivative of each term in the power series. So that's what we're gonna do. So let's do that. um, well, x to the n is like an exponential function. So to take the derivative of something in that form, you just apply the power rule for derivatives. So the rule says you bring the exponent to the front. Well, let me write the series sign. So you bring the exponent to the front, and then you subtract 1 from your exponent, right? So there's the derivative. Okay. So that's how you take the derivative of that power series. And then, yeah, so this is the power series representation of our function. And then our interval of convergence, it was -1 to 1. And then taking the derivative doesn't change that. So our interval is still -1 to 1. Okay. So this is your answer. This is the power series representation, and then your interval is -1 to 1. Yeah, I mean, if you just think about what this power series looks like, it's just 1 plus x squared, and so on, right? So if you're just taking a derivative of this, then you get 0 plus 1 plus x plus 2x, and then so on and so on. So essentially, you're just doing this to each term. All right. Yep. So far, our goal has always been to get these questions in the form of 1/1 minus x. However, there's many ways to get to that form. So you can use algebra. You can just rewrite it. You can take the derivative if you need to. So yeah, many different ways. Okay. Any questions on that? All right. So now that we did an example where we had to rewrite it as a derivative, what do you guys think we'll look at next? Yeah, integrals. So let's look at this example here, and then we will ask the same question again. So taking a look at this function, which says ln of 5 minus x, um, our goal is the same. How can we get that function in the form 1 over 1 minus something? So what do you guys think? Integrate. Um, uh, yeah, so let's just verify that. So when we take the integral of ln of 5 minus x, what do we get? Um, almost. So be careful, do a u substitution because the inside is 5 minus x. So if you let u equals 5 minus x, du is actually negative 1 dx. So it's not actually just 1 over 5 minus x. You have to account for the negative sign. So this is actually negative 1 over 5 minus x. Do you guys see what I did there? Okay, anyways, so, well, I kind of don't want the negative sign there because the form we wanted in doesn't have a negative sign. So let me just move the negative sign to the other side. So it's negative integral of uh, ln of 5 minus x is equal to 1 over 5 minus x. Okay. Yeah, what's up? Isn't d dx of ln of x 1 over x? Was it? No, I think it was the other way around. Pretty sure the derivative of 1 over x was ln of x. Let me just verify that, just so I verify I'm not going crazy here. Derivative of no, yeah, you're right. So derivative of ln of x is 1 over x. So the derivative of ln of x is 1 over x. Okay. Yeah, I don't know. I must have been going crazy. Anyways, let me just make sure that our work is fine. If it's not, then let me just correct it. uh, Yeah, okay, yeah. I totally had it the other way around. I'm sorry, guys. The integral is supposed to be on the other side. All right, I have to redo this. Yeah, my bad. So it's 1 over 5 minus x, but we take the integral of the side. uh, Goes to show you that sometimes I can't do this. All right. So yeah, help me out here, guys. So we're trying to take the integral of 1 over 5 minus x. Uh, should be ln of something, right? Yeah, okay. So ln of 5 minus x. And then there should be a negative sign, right? Because u would be 5 minus x. So a negative sign here. All right. I'm pretty sure this is right now. Okay, so I'm going to bring negative to the other side. Ln of 5 minus x is equal to negative integral of 1 over 5 minus x dx. All right, so this is fine because we have ln of 5 minus x here. So h of x is equal to ln of 5 minus x, which happens to be equal to negative integral of 1 over 5 minus x. All right. Yeah, this does make sense because I designed the question to like have you integrate it. So yeah. All right. And then 1 over 5 minus x. Didn't we do that before? Yeah, I'm pretty sure we just did that. Let me see. Yeah, I'm pretty sure we did it, but I erased it, so guess we'll just do it again. So h of x is negative the integral of, so we want to get 1 over 5 minus x in the form of 1 over 1 minus x. So this is 1/5, 1 over 1 minus x to the 5th, right? Okay, so now the parentheses, the term inside the parentheses is in the form that we want. So we can write the power series for that. This is negative integral 1/5. This is the power series of x to the x over 5 to the n dx, right? Okay, so let me just bring the 1/5 inside inside the series. So this is negative integral more space. This is summation of n equals 0 to infinity of x to the n over 5 to the n plus 1, right? Because this 5 combines with that 5. So this is what we have so far. Okay, I think this is as far as we're going to get for simplifying it. The next step will be to take the integral of this series. So just like for derivatives, when you take derivatives of a series, you just find a derivative of every term in the series. So when you're trying to take the integral of a series, then you just take the integral of every term in the series. So who remembers how to take the integral of a polynomial? So for derivative, it was you bring the exponent to the front and you subtract one from the exponent. So for integral, what do you do? So for example, if I want to integrate, say, x to the third, how do I do that? um, so 3x squared would be the derivative, not the integral. So for integral, this would actually be, this would become a 4, and then you would divide by 4. So this is actually the integral. And then the general pattern for integrating is you add 1 to the exponent, and then you divide by your new exponent. Yeah, plus c. Yeah. So we're going to do that with our series. So right now, our series is x to the n over 5n plus 1. If we take the integral of that, we're going to add 1 to the exponent, right? So it's going to be x to the n plus 1 now. And then we're going to divide by our new exponent. So now we're going to divide by n plus 1. Okay. So this is our power series now. And then you will have a plus c, because we just integrated with no limits of integration. So you need plus c here. And then I think someone said that, yeah, so our interval of convergence was -5 to 5, because that's what we had for the previous time we were doing this power series. And then when you integrate a power series, that doesn't change your interval of convergence. So this is still the interval, -5 to 5. Okay, so this is the power series representation of our function, and then our intervals from -5 to 5. We have one less thing to do, and that's to solve for c, right? Because we can't just leave it like this. We need to find out what c is. So how do we do that? So what we just found out is that the power series representation for ln of 5 minus x is equal to this power series. But we need to find what c is. So any suggestions? Plug in a variable x aside interval. Yeah, yeah, that's what we do. So I think in this case, 0 is probably the easiest, right? So recall that this equation we just wrote holds for these specific values of x. So we can just plug in a value of x to solve for c. So I'm just going to choose 0 because that seems the easiest. So let's see what we get. We're going to get ln of 5 minus 0 is equal to negative summation of 0 to the n plus 1 power over 5n plus 1, n plus 1, plus c. So that just makes it ln of 5 equal to, well, if 0 is in your numerator, then it's all just 0. So this is just c. Okay, so the value of c is ln of 5. So let's replace c with our answer. So instead of writing plus c, we can write plus ln of 5. Okay. Okay, so there's our final answer. The power series representation for ln of 5 minus x is this power series here. And then this is your interval of convergence. This one looks a little bit weird because you just have like a little constant hanging out of the summation sign, but that's fine. There's nothing you can do about that. All right, any questions? Wouldn't there be a hole in the interval? I don't think so. It's undefined at n equals -1. Yeah, it does seem like it because, oh, no. No, it's fine because the interval of convergence, these are x values, not n values. Yeah, so whatever value you pick actually only goes here, not into the n. N is the index for this, yeah, for the series. All right, so this is all the examples we have for today. So just one more summary. You want to memorize this formula here. So this thing, memorize that. And then for every question that asks you to do this, try to get it in this form, right? That's the main goal, this form over here. And to get it in that form, you might have to rewrite, take derivative, or take integrals. Make sure you memorize what the integral of ln is, because apparently I forgot. And then once you get in that form, then you can just use this formula here, and then just like simplify everything, and then use this to find your interval of convergence. Okay. All right. Any last questions? All right. So before I let you guys go, let me just talk about the remaining classes for the semester. So let me pull up the syllabus. screen. All right, here is the syllabus. Okay. So today we just did 8.6. So that was today. That was 11/24. The next time we meet is when? Next Tuesday is December 1st, right? Yes. Okay. So December 1st, we're going to cover. We're going to cover Taylor and Maclaren series. So this is 12/1. And then I'm gonna try to like put some stuff from here into the lesson as well, but you know I'll see how it goes. And then I know 12/8 is the last day of class, which means uh, December 3rd is the second to last day, which means we need to read for the exam that day. So 12/3 is review for exam 3. And then 12/8 is the exam 3. Okay, which means there's going to be these 3 topics, which we are not going to cover from the syllabus, and you know there's nothing I can do, right? Because we ran out of time, and no one knows how to deal with it because like you know we're teaching differently. So here's what I'm proposing. I know a lot of you guys are planning to take stuff like linear algebra and Calc 3 and what was the other one, like Math 255 or whatever. So those courses actually use topics from these sections of Calculus 2. So for those of you who are interested, you know, who are going to take those courses, I am going to basically make some recordings of just me lecturing about these topics, okay? And Calc 2 is a prerequisite for linear algebra. Well, not directly, because Calc 3 is a prerequisite for linear algebra, so technically Calc 2 is as well. But yeah. Linear algebra is 260. That's the math major one. Is that the one you're talking about? Linear algebra 2, math 260. No? I'm assuming you're taking 160, is that right? Yeah, so 160 is basically linear algebra, but they call it matrix algebra just to like you know give it a different name. But yeah, 160 I don't think requires Calc 3, so I don't think that requires Calc 2 as well. So you're probably good. So you probably don't need these for 160. But anyways, like I was saying, for those of you who are taking higher level math courses like 250, 260, and 254 and 255, you will need to know topics from chapter 9. So I'm going to make recordings of these topics, just like me lecturing, and I'll record it through Zoom, and I'm not gonna have any of you guys attend because I don't think that's necessary. And then I'll just upload these onto probably Blackboard. And then for those of you who want to learn this stuff while you're in Calc 2, you're free to just go onto Blackboard and just watch, okay? So I'm not gonna lecture these topics, but I'll make resources available. Because I know like it's, you know, we're supposed to teach you this, so I have to do something. But there's unfortunately not enough time. So well, the reason why I chose 8.7 is because that's actually, in my opinion, that you need that regardless of where you're going. So I have to do 8.7. 9.1 through 9.3, those are for some people, which is why I'm providing it. Okay. And then 12.3 is exam 3 review, and then 12.8 is exam 3. So that's the plan for the rest of the semester. Just wanted to update you guys. All right. So yeah, we'll stop here for today. Do the homework if you would like. If you don't want to, then whatever. And I'll see you next Tuesday. Yep. Have a good Thanksgiving, everyone.